Okay, so let's switch gears and move into a totally new topic. So up until this point, we've talked about estimation, essentially, and different forms of estimation, maybe a predictive estimation, or we're just going to try to infer theta. Okay, so I think what we've seen so far is a lot of agreement, at least asymptotic agreement. So if we use reasonable priors, then the estimates we get are something like the old estimates we saw in Stat 101. So like for the normal example, maybe if I were trying to infer the mean, I would use something like X bar. But a Bayesian might penalize that a little bit as well, or have some subjective information to go into things. Or maybe if you use the flat prior, the limit of the conjugate prior, your best guess at mu is X bar. And so if you had some subjective information, you might encode that using the conjugate prior, and you would still have something like a weighted average of X bar. And I think that you'll see classicists and Bayesians come up with things like that, but for maybe differing reasons. But at the end of the day, they come up with something similar. Hypothesis testing is different. So hypothesis testing is where the agreement starts to break down quite a bit, but not for all types of hypothesis tests. So some hypothesis tests, a Bayesian and a non-Bayesian, totally disagree with each other. And in some cases, they will agree with each other, or at least closely. And so we want to study both those cases and understand that they're different from the onset. So let me just give you an example. So these are some common examples. So basic setup is you see data from some model, and then you're going to make some questions about what is theta. And so this can all be scaled up to multiple hypotheses, but ultimately what you're going to do is you're going to compare one hypothesis to another hypothesis. And so, and the way you compare things differs depending on which branch of statistics you follow. So we're going to talk about a lot of this philosophically, and then we'll get down to how do you actually compute everything. And later on, we'll check to see which methods work better. So we'll do a full-on comparison. So what I'm going to do later on, instead of just talking about one parameter theta, we're going to build up lots of parameters in like regression models. And you're going to try to identify how I've generated the data. So I have kind of increasing skill level hypothesis tests where I'll give you something really simple, you know, where n is big and p is small and the space is all orthogonal, and you'll probably be able to nail my model, you know, how I've generated the data. When you start building in interactions and things like that, or the x's aren't orthogonal to each other, there's a lot of disagreement on what the correct model is. So I'll let you know eventually what models I've generated everything from, but I want you to try to guess later on. So that'll probably come up in a couple weeks. So we need to learn the basics first. Okay, so you see data out of some model, and then you have some questions. Does theta belong to this space, or does theta belong to that space? And this might seem a little bit abstract. So we'll just lock down some examples. And certainly you can need a couple of these before. So for instance, you might have xi's are coming from a normal model with mean mu and some variance sigma squared. And we'll say, just to make this easy, so we'll say this is known. And so this is my model parameter right here. This is theta. And so I might have a couple different questions about theta. So possibly I might ask this question. And this is probably the most contentious question in all of statistics. So the null hypothesis is maybe something like this. Theta is equal to some pre-specified value. Theta naught. So, I said theta, but what I really want to talk about is mu in this example. So is mu equal to some value mu naught? For instance, is mu like 5? So, or 0. Very common question. So, versus the alternative. And sometimes people call this H1, but I like HA. And sometimes I'll switch between H alpha and HA. So all of that means the same thing to me. Mu is something different. So this is like the Stat 101 question. So this is the one that everybody dwells on. There's some other questions that are similar. So a similar question might be, I might have xi's coming from some normal. I'll call it mu x. I'll say there's some sigma squared right in here. And I might have another process where yi's, and I'll say I goes from 1 to n. Let me change the index here. Yj's, maybe from some other process I observe something. We'll make this really easy. I'm going to pre-assume they have the same variances. So, and then you might have some question about this. So I observe some data, say j goes from 1 to m. So these numbers don't need to be the same. So I can go and experiment and grab some data from process 1. That might be this. Then I go grab some data from some other process. I get that data. And then I could hypothesize about the processes being the same. And so if we agreed that everything was normally distributed and the variances are the same, we might ask this question. Is mu x equal to mu y versus something else? Mu x is not mu y. So the idea is we're checking to see if the two processes are the same processes. Do you guys know how to solve that problem? It's not too hard. So every Stat 101 class will teach you how to do that. They'll at least give you some procedure for doing this. I would say this sort of test is very similar to this test in spirit. And in fact, they have all the same properties. So here's another question. If we ended up saying these two different variances are different, but they're known, do you know how to solve that problem? How do you do it? What do they teach you in Stat 101? Is it a hard problem to do? No. So what most people will do is they'll just rechange this to mu x minus mu y and set that equal to 0. So you're really testing, is this parameter the difference between means? Is it equal to 0, which is very similar to that. So where this thing right here would be a 0. So that's not a very contentious problem. So if we all agree on everything's normal, I think the contention is whether or not we know the two variances. So maybe these are known right here. And so it turns out you can come up with a p-value for that sort of thing, and we have to discuss whether or not that p-value is meaningful to us. What about this problem, where these things are unknown? Do you know much about this problem? What do you do if the variances are unknown? I'm just trying to gauge what you guys know already. Have you studied that problem? I studied it when I was a freshman in college. They teach it to high school students. So if you've ever taken any stat class before that has any inference involved, you've studied this problem. Has anybody never seen this problem? Have you taken Stat 101? Any stat class before? Is this your first stat class? Statisticians in the room. Have you seen this problem before? What is this problem called? Huh?
Some data.
Yeah, so this would be like a t-test. So you're setting up a t-test in this. So it would be a z-test if you knew what the variances were. And if you're going to integrate out the variances, you're going to get a t-distribution. I might throw the variances on a precision scale, integrate them out, and turn all my inferences about mu into an inference based off of a t-distribution. So I'd be comparing two different t-distributions. This is t-testing. So this is the two-dimensional analog of ANOVA. So this is probably the question most people in all of science study, is this thing. This is what you see most tables built up on. So when those two variances are unknown, what do? So usually you come up with some sort of a test statistic. So you might do something like this to measure mu x and mu y. I might get x bar and y bar. And then I divide by the standard error. And the standard error for all of these different versions of problems change a little bit. So the standard error, if I knew what mu sigma x and sigma y are, the standard error involves both of those things. And you're probably going to scale them to n and n. You probably add those two things together. So that's the typical sort of thing. What do you do when the variances are unknown? So some sort of a t-test. But what do you do to get the standard error? Say it again?
The sample variance.
Come up with the sample variance. But you don't know, so you just combine everything together and estimate the variance?
I think you first individually estimate the variance and then you pool it together.
You pool them. Yeah, so you do that pooled thing. Is that actually a t-distribution still? Turns out the answer is no. So that's not a t-distribution. So if you ended up pooling, estimating both of these variances with your typical variance estimators, and we'll write them down when we get farther into this class. But you would end up looking at the sum of the xi's minus x bar squared, and you would scale it somehow, and that would estimate sigma x. You do the same thing with your y's to estimate sigma y, and somehow you combine those two things together to come up with a common pooled variance. Do you know why they do that? They do it so they can cram it into a t-test. And it turns out it's not t-distributed. So has anybody heard of this thing called the Satterthwaite correction or the Welch correction? How does that work? Just in a sentence or two. What happens in that? Stat 101. You teach this to freshmen.
You adjust the degrees of freedom.
Yeah, you adjust the degrees of freedom. So you try to match it to the closest t-distribution possible. So it turns out, in some cases, that statistic that we wrote down is t-distributed. So if the sigmas are the same in both processes and everything, you can divide by the standard error and come up with it exactly. This would be a z-score. So you probably look at something like this, absolute value of that thing. And you get a normal distribution for measuring that thing, and everything's fine. It is normally distributed. When the variances are known and different, you can combine those two variances and create a t-statistic. And so and compute a p-value or do whatever a Bayesian does with that. So the thing that's not a p-value, I'll show you what that is soon. If the variances are not known and you estimate them and you work with that test statistic right there and you come up with a pooled variance estimator, it's not t-distributed. That is not, it's just false. And in a lot of Stat 101 books and even higher up books, they tell you just blindly, you just plug this, look up in a t-table, check your critical points, and then make a decision based off of the p-value calculated. It's not actually t-distributed. The Welch thing is trying to get it to be the closest t-distributed thing. So the idea is this thing right here on top has something to do with the normal distribution, and the thing down in the bottom has something to do with a chi-squared distribution. It's the square root of a chi-squared divided by the degrees of freedom. And so that turns out to be t-distributed. We'll look at that later. So this is just a review so that we can jog our memories about what we maybe learned before. It turns out they lied to you. If you pool everything and you do the Welch thing, why do you need to match it to the closest t-distribution? Because it's not t in the first place. Does anybody know in this case where these are unknown and you need to estimate them and you use a statistic of that form and you pool the variances? Does anybody know what the actual distribution is called?
Non-central.
What's that?
Non-central something.
So it's not that. I know what you're thinking about, the non-central chi-squared thing. It's actually a real distribution. It's called the Behrens-Fisher distribution. So has anybody heard about the Behrens-Fisher problem? It's one of the classic problems in all of statistics. And so it turns out that test statistic, when you do the pooled variance sort of thing, and we'll discuss different forms of pooling, but I would like us all to stop doing it. So I think if you base your p-values off of a distribution that the statistic isn't actually even distributed that way in the first place, and you come up and you make these decisions, possibly we're doing everything wrong out in all of science. And so when you do a rejection on a hypothesis, you might not be rejecting the hypothesis itself, you might be rejecting your model. And so your bad modeling assumptions. And I suspect that a lot of people out there are rejecting their pooled variance estimator. So they're saying, it's not that. But then they make a claim about their hypothesis. We want to be able to distinguish all of those things. The Behrens-Fisher distribution, if you were living in the 1930s, it's a 4-parameter distribution. You need to know 4 things. Where the t-distribution, you don't need to know that much. You need to know the degrees of freedom. So, and then whatever that x bar minus y bar thing is, your test statistic. So you couldn't table it. You know, you can kind of imagine, even for like a t-table, the tables are pretty big. And if I tried to go over all degrees of freedom, the table set would be even larger. And so, you know, a lot of times we use the normal approximation to get away from that. If you had 4 parameters that controlled everything, the tables would be huge that you would use. And back in the 1930s, this is a big deal. But in 2022, I don't think that should be a hindrance because we have computers. We don't look at tables anymore. Does anybody ever look at one of their tables? When's the last time you looked at a Z table or a T table? 2012. That's a good answer. Anybody do it more recently?
When I grade intro stat courses.
So you teach it, or the instructors still teach that stuff?
Sometimes, yeah.
That's sad. So we need to get rid of that. So I used to grade for classes like that too, where I would sit there in the tutoring center and I would teach people how to read their specific Z-score tables. It's like, oh, is this the one where it adds up to the left or the right? And what do I do if there's like, I'm doing the 2-sided test and I need to get the middle? There's always like a little picture on all the Z-scores, and I would have to train people to look up things in the table. I thought it was ridiculous. So I still do think it's ridiculous. Anyway, so people still are dwelling on this sort of stuff. There's huge issues in this problem. Let me just go back to this simpler problem. This is called the Sharp test. Sharp testing. Some people will call it the two-tailed test, but they're describing a procedure. And so I don't think it's a good name for it, but basically this hypothesis right here takes on a value at a point, and that's what we're calling sharp. So sometimes people will call this the simple versus complex or composite hypothesis. Well, what do you think of this test right here? If somebody came in with this data, xi's are coming from something they got big N, so they've seen a lot of things. Big N is like 31, right? That should be big enough. Maybe. What do you think of that test? If somebody came in and they asked you this. Xi's are coming from a normal distribution, and we feel really confident about this thing. It's normally distributed. And they asked you this. What would you tell them? Is mu equal to mu naught or something different? You've all performed this test. At least you should have.
It's kind of a strange formulation because mu was on a continuum. So to say it's exactly 1 point, it's like probability 0, right? That's continuous.
Yeah, it's kind of like that. So it's like, what do you think people mean when they're asking this question? This is the most common question in all of statistics.
I think people use it in regression so much that they're used to mu 0 just being 0.
Yeah, maybe. So maybe they do it on an intercept. We can look at that in a moment and get a little bit more complicated. But if somebody came and they asked me this, I've got this data and I've got this hypothesis, I'd say I'd leave that one. So this set is so large compared to this. What is the probability that you would have even asked about the right mu? Mu naught? 0. So is this really even a valid question? And my answer to it is no. That's not even a reasonable question to ask in the first place. If it was this problem right here, I'd say just estimate mu and tell me what you think mu is and what valid ranges of mu are. Obviously, if you get into high dimensional regressions, that's a harder question to entertain because I might be doing a lot of testing on all kinds of regression parameters. And so you might need some procedure because you just can't think about everything and show all of those intervals and make all of these judgments. What do you think people mean when they're asking this question?
Close to this value.
I think so. And so I think the real question is it close to mu naught? And what Bayesians and non-Bayesians are really disagreeing on is their notion of closeness. And that's what we need to really hash out. Why this divide is happening, I would say, of course there's a divide here and all kinds of paradoxes because it's a silly question. So, but I think we could re-engineer that question and say, is it close to mu naught for us to accept mu naught as a reasonable candidate? And so, but we have to define closeness, and the Bayesian and the non-Bayesian define it totally different. So we'll look at that. There's other hypotheses out there. So here's what some people call the one-sided hypothesis. So I might have the same data, but I might ask a different question. Is mu greater or equal to mu naught versus is mu less than mu naught? Just put the equal sign on one of them. Everybody puts the equal sign on the null space because that's actually where you have the most power to test everything is at actual mu naught. We'll go into those details. Is that a reasonable question? I think that's a reasonable question. So, and because the comparison is fair, it's at least reasonable. The size of this set and the size of that set are the same. Everything greater off to infinity and everything less than mu naught off to negative infinity. And those two sets are exactly the same size, so I think that's a reasonable comparison. Unsurprisingly, probably, is Bayesians and non-Bayesians kind of agree on this problem. And I think it's because of the question being asked. It makes sense. There's other questions. How about this question? So the interval test. Or the interval hypothesis test. So I might ask a question like this. Is mu an element of this interval? Just come up with two possible values right here. Or is mu not in that set? And I'll write it down this way. mu1, mu2. So basically the question is, mu1, mu2, is mu in here, or is mu out here? That's the interval test. Have you ever done that test before? Has anybody ever done this test? Have you? I mean, it's either yes or no. So,
paper about it.
you wrote a paper about it?
Right.
Cool. How do you do that test?
Sam, you want to help me out?
I would refer you to the paper.
Yeah.
You guys must be really smart. That's what I do to people. Yeah, go read the paper. So, did you do a classical thing? So yeah, my feeling about this is if you cannot explain why this stuff works, you should not be doing it. So, and I think a lot of people are out there peddling these tests. They don't really understand all the issues, and they're just bombarding journals with nonsense. I like this test. I really like this test a lot. I think it's a totally reasonable question. So it's kind of like this question right here, but we're being much more specific about what we mean by close. So maybe mu naught's like in the middle, and I think, well, if it's over here, maybe that's close to mu naught. If it's over here, maybe that's close to mu naught. And you have to really think about what these bounds are. And so that would have something to do with the context of your problem. And I think that's why we don't teach that a lot, because you have to think about it in the context of some problem. So, and people are just too cowardly to come up with these points right here and say, I think that in this interval, anything in there would be about the same to me for my problem. We'd have to address, like, how did you come up with those points? But maybe if you were a physicist or something like that, and you're coming up with some contraption in the laboratory, and you knew what the measurement error on your machines were, the things that you're measuring, and you could calibrate that, then maybe those are defined by the measurement error. You know, so maybe you'd say, my hypothesis is mu naught, but I know what the measurement error is. I can measure things to some degree, and maybe I'd use those to calibrate mu1 and mu2. I like that test a lot, but it does make you think about what it is you're testing, and you would have to defend what your mu1 and mu2 are. Bayesians and non-Bayesians totally disagree on this problem as well. So let me at least tell you how a Bayesian deals with this problem first. So let me ask you, if you're a Bayesian and you're going to try to answer that question, what would you do? Yeah. Posterior probability, exactly. So for Bayesian, this is a really easy question. So what you might do, we'll talk about a non-Bayesian solution to it. They never show you in the textbooks because it's embarrassing. So it doesn't make sense. The p-value sort of thing that you come up with is what we say is incoherent, and I need to teach you what that word means. So, but there is a uniformly most powerful test for doing this, a Neyman-Pearsonian procedure. We'll look at it later. I need to tell you what all that stuff means. And the p-value, you cannot interpret it as a measure of evidence against the null hypothesis. So we'll look at what that test looks like. So the Bayesian does this. Integral, I'll look at my posterior distribution on mu, given x. I might need to justify something about my priors on this, but if you didn't tell me anything, I'd be inclined to use a flat prior right there. So I'd use a flat prior on doing this test, come up with this thing. I could probably defend what that distribution is. Probably it's going to be a normal distribution centered at x bar, and it's going to have some variance attributed to it. So that would be this thing under a flat prior. And I could probably defend all of those things reasonably well. I could convince classicists that that was a good distribution to base everything off of, because they use that exact same distribution. So, and then I would just integrate between mu1 and mu2. And so that would be the probability that mu lives between mu1 and mu2, given all of your data. And I can write that out like this. This is the probability of the null hypothesis, given x bar. And that's what a Bayesian is always going to give you. They're going to give you a probability distribution on the null hypothesis itself. Non-Bayesians do not do that. They're not giving you an actual measure of the hypothesis. They're giving you a testing procedure, and they're calibrating error rates, which is totally different. Sometimes they coincide with what a Bayesian does. So in the one-sided test, we have the same measure. Their p-value would be my posterior probability usually. In the interval test, there's no connection. So between what a non-Bayesian is doing. And in the sharp test, there's no connection as well. So total disagreement. Let's think about the sharp test just real quick again. What would a Bayesian do? What do you think a Bayesian does? Can we apply that same idea? I mean, you could, right? So this is meant to be a joke. This is a joke. So don't do this. But maybe you do something like that. I've come up with my posterior distribution. Same posterior distribution that I had over here. Use the same prior. Plug in a mu. Integrate against mu, mu naught to mu naught, and even I can do that integral. That's 0. So I like that answer. Like I think that is the answer. But it's not answering a reasonable question. Is mu naught? No. So Bayesian needs to do something a little bit different than that. And so they need to define closeness to make this make sense. So this is not what they do. But I would say in the way I see scientists operate out there when they're doing a statistical analysis, most of the time, so this might be an overgeneralization, they're looking for small p-values so that they can reject their null hypothesis, so that they can publish something. And so that seems to be their utility function, you know? So I need p under 0.5. If you just want things to be small, you couldn't ask for a friendlier device. You could reject everything. So obviously, this is not exactly the question that people want to ask. So we need to be a little bit more careful about that question. Okay, let me show you what a few things that Bayesians do. So this is true in all cases. So we'll gear up to answer all of these questions and address all of these conflicts. This is going to be the black eye of statistics in 50 years, I predict. So people will be like, I can't believe people did this, you know, sort of thing. So the p-value calculation. We'll study a few papers too that criticize what's going on with p-values. So Bayesians like Bayes factors. And this is for all hypothesis tests. So Bayesians will compute this thing to address all hypothesis tests. So the Bayes factor is this. It's a ratio. I'm going to integrate f of x. So this is all of my data. So I have all of my data plugged in there. We'll go back to our notation with theta and just kind of discuss the general problem. And then what they'll do is they'll integrate over a prior on h naught. We're going to need to have lots of discussions about this. And I'm going to integrate in the null space. And I'm going to compare it to something very similar, but I'm going to integrate over the alternative space. Bless you. So this is what Bayesians do. So I want to just point out, this is the margin. I'll just write this down. This is f of x under h naught divided by f of x, where I've integrated over the alternative space. So these are just margins. So we haven't computed an explicit posterior probability to do everything. I'm just looking at the marginal support under both model spaces. So how would you interpret this quantity? So keep in mind, all we're doing is we're taking our sampling distribution right here and thinking about it as a function over theta, and I'm integrating over theta. So I've upgraded theta to a random variable, so now I'm allowed to integrate over it. And so this prior has to add support just to the null space. So this is something we're going to need. So usually, we'll need our integral over our prior. It's going to need to integrate to 1, where theta is in the null space. And we'll need this. Now, I wrote this word usually. You don't always need that. You don't always need to be using a proper prior. But I at least want to start us off and think about most of the time we need a proper prior. So you might go back to this example right here and say, is it okay to use a flat prior in this? And in this example, it is okay. But if we did it for the sharp test, it would be a terrible thing to do. So we're going to have to say more about the usually part. But usually we're going to need proper priors. And if we just look at what this is, if these are proper priors, all this is just an averaging. So all we're doing is we're comparing how well, on average, the data fits the model in the null space, and we're comparing it to how well the data fits the model in the alternative space. And we're comparing everything on an on-average sense. So this is just averaging. So you could rewrite this, if you like, and say this is the likelihood function. Obviously, I can multiply everything by any constant I wanted, and they will cancel out. So the way we write down the likelihood has to be the same in both the numerator and the denominator. All arbitrary constants need to cancel. And so you're going to need this if things don't cancel in your prior space properly. We'll go through some detailed examples on that. So this is just an average, a comparison on average how well the data fits the model on average. Here's another contraption. So Bayesians do this, and they like to compare things on average. Naaman Pearsonians, aka classicists, you might say, aka a frequentist. There is a frequentist interpretation to doing this. We'll talk about that soon. But non-Bayesians often look at this creature. So they take a likelihood function, and they maximize this over the null space. And they compare this to the maximum, where theta is in the alternative space. And they compare these two things to each other. So they look at the likelihood function and they maximize it. And they do the same thing in the denominator, but they do them over two different spaces. So if this was the sharp test for H naught, there's only one value you could even plug into this. So that's the easiest maximum to take. Very easy maximum to work out. And then down in the bottom, usually you would end up plugging in something like the MLE down here. And it turns out you could make this the union of H naught and H alpha. You would have exactly the same properties in your test. If you've taken an inference class, my inference class, you'll understand that. So this is called, anybody remember? There's one more word. Yeah, it's the max likelihood ratio test, statistics. So this is the maximum likelihood ratio test. And it seems like if I look at this thing and I look at that, they're kind of similar to each other. So it seems like maybe there's going to be some agreement because of the similarity between this. And we'll point out that if your likelihood surface looks something like this, so let's say your likelihood, if I ended up just plotting it, if it looked something like this, very peaky. So you have a lot of data averaging over this likelihood, like you would do right here, in maximizing it, are about the same things. So they're not that different. So, and you can kind of imagine this if you took this to a more extreme limit, where this thing was just super peaky, where that actually just converges to a point mass. So if n went to infinity, then the average and the maximum would be exactly the same, because it's just a point mass. So averaging over a point mass and maximizing a point mass are the same things. So Bayesians and non-Bayesians will disagree when the likelihood function looks like this. when it's flat. Very flat and wide. So averaging over this and maximizing in a point are very different. And so a Bayesian and a non-Bayesian will disagree with each other when the likelihood function is flatter and there's more uncertainty. So averaging and maximizing are different things. Let me just ask you a question. Which one do you think is more reasonable? Averaging the likelihood function or maximizing it? So let me just ask you in a slightly different way. So you can imagine you're a scientist. You can think about what you actually want to know. So I have two different classes of models. Do you want to compare the two best models in your classes to each other? Or do you want to compare the average models in your two classes to each other? What do you think scientists actually want? Comparing the best model in their candidate space or comparing the average models? I don't know the answer either, but usually we don't ask our scientists, what would you actually like to explain to each other? So on average, how things compare, or your two best models? I tend to think scientists probably are thinking about this, that they're like, I just want to know the two best models, how they fit the data, and I want to compare those. So I think oftentimes they do want this, but what they do with this might not be what they intended in the first place. So in some cases, this thing and the likelihood ratio test statistic are really close to each other, and in some cases, they're really far apart from each other. Lots of things to think about. Let me give you an example. So consider this. I'm going to say yi's are going to be equal to alpha plus beta xi plus error, where these errors are IID errors, and they are normally distributed. And I see a bunch of data. So this is just simple linear regression. So I think everything we need to understand about regression, we could understand through this simple model. And later on, you'll play around with bigger models where there's more x's. I might have a hypothesis. Alpha is equal to 0 versus alpha is something different than 0. Very common sort of hypothesis. Is the intercept 0 or not? Now, what I usually think is you shouldn't ever test that. Just put the intercept in your model. Throw it in there. It's really important, your intercepts in your models. So when I walk through and I go to the biology department, sometimes I'll look at their posters hanging on the walls, and they'll do something where they'll report R squared, and they'll tell us what the interpretation is of it, and you'll notice that they've not put an intercept into their model. It destroys their interpretation of things like R squared, the amount of variance explained in things. So I think you should always put the intercept in there. And if you say, well, I don't have enough data to estimate it, you probably should stop and go get more data and think about what you can actually test. But we can still use this as an example, just to kind of see what's going on. So here's what a Bayesian would do if this was their question. So they might do something like this. The Bayes factor is going to be the integral of my likelihood function. And this would be pretty easy to write out. I guess we can do this. So this will be the product. I goes from 1 to n. 1 over root 2 pi. And I've got a sigma in here. E to the minus 1/2 yi minus alpha plus beta xi squared. So this is the mean of everything, divided by sigma squared. And then I need to integrate over the null space. So I'm going to say, I'm going to put some prior on beta. You're going to test this. And then I'm going to have some prior on alpha. And if you'd like, maybe I could call that a joint prior. D beta, D alpha. So this is going to be a double integral. And I'm going to integrate over all of beta, whatever that is. And then I'm going to integrate over alpha in the null space. And then I'm going to compare it to something similar. Just put this in braces. I goes from 1 to n, 1 over root 2 pi, sigma e to the minus 1/2 minus yi minus alpha plus beta xi squared over sigma squared. That likelihood function is the same in both models. And then I'm going to need some prior. I would integrate this over all of beta. So this isn't being tested, so the integral over beta is exactly the same. But this is going to be alpha in your alternative space. So when I do this integral right here on alpha, this is pretty easy to do up here. So alpha only takes on one value in the null space. It's 0. So that's a very easy integral to do. And I can just get rid of that thing. Put a 0 right there. That's what we actually mean to do. So I could get rid of that right there. But then I have alpha being free over in this space. So the big question is, how do I pick these priors? So let me just write them out a little bit differently and say maybe we're going to use independent priors like we've been doing in all of class. So I might have a prior on beta and a prior on alpha, but I need to be specific about the null space right here. I've got a prior on beta right here, and I've got a prior on alpha in the alternative space. So I think we could maybe talk about the prior on beta pretty easily. So let me just ask you guys, which prior on beta, if nobody told you anything about beta, what would you use? What's that? Flat prior. So maybe this is flat. Maybe this one's flat. So I'll say proportional to 1, and this one's proportional to 1, right here. So this thing right here can only take on values at one point. And so how I smear mass over that one point, there's only one way to do it. So, and it's to place all your mass on that one point. This set's really tiny right here. So there's only one way to smear that mass in here, so maybe I get rid of that right there. And I just say, hey, the probability that alpha is 0 in the null space is 1, because that's what we're testing. So I just replace that with a 1 right there. Quick question, what prior do I pick for this? Maybe I replace that with a 1. I write down that this thing right here, I'll write it down as the probability of alpha equal to 0 in the null model. This is equal to 1. That's what we plugged in right there. Again, there's no question about how to smear mass and average over a point. So no matter how you think of it, just as long as you put mass at that point, we're all going to do it exactly the same. So there's no shape I need to think about. But what about this one? What prior would you pick? I can wait. It's an interesting question, isn't it? Can I just pick the flat prior right there? No, you can't. So if you ended up saying, I'm just going to make it proportional to 1, remember what we did in all our other things. If we made everything proportional to 1 and we had that prior, there was a numerator and a denominator where everything canceled. when we computed a posterior distribution on alpha. And it would have been exactly the same if I picked the number 10. That's also a flat prior. And I could have had that 10 in both the numerator and the denominator, and they would cancel each other. And it didn't matter which number I plugged in there. Here it totally matters. So if I plugged in 1 or I plugged in 10, I get totally different answers. They're off by a factor of 10. And so we can't do that. So you cannot use an improper prior here. So improper priors here are not allowed. But we are able to use an improper prior on beta. And the reason being is that beta appears in both model spaces, and beta has exactly the same meaning in both model spaces. More importantly, the arbitrariness of this prior that you plug in here, if you wanted to use your flat, non-informative prior, it's Jeffrey's, all kinds of good reasons to pick it, they cancel each other. So for parameters that don't appear in both models and have exactly the same meaning, you cannot use a flat prior. And so to some people that's troubling. And so the question is which prior do you pick for that? And we'll come back and we'll address that question. So we need a different notion of prior. I'll also just write down, and we can come back next time, improve this. So what you can do is you can compute the posterior probability on the null space given all of your data. And this is going to be equal to 1 plus 1 minus pi naught over pi naught, base factor inverse, invert all of that. These are going to be your model priors, how much mass you're putting on both model 1 and model 2. Those are different than the continuous priors that we're using on the parameters. So what a Bayesian will also do is they'll weight the model itself. And so if I put equal mass on both models, these would cancel. But there's a connection between the base factor and the posterior probability of the null space. We'll come back next time, pick up there, prove that that's true, and then we'll look at some more examples. So I think what we need at first is just some examples, see what we're doing, and then we can discuss all of the issues. And there's plenty of them. Okay, that's it for now. So enjoy your weekend.